Welcome again to our lecture course on the early universe. Actually, today is our last lecture, and we have started some time ago with discussing perturbation, so discussing inhomogeneous universe. So I reviewed the Newtonian case, in particular the Jeans theory for the static universe, and then we extended it to the expanding universe, but still in the Newtonian limit, and then went to general relativity, which is of course the important framework. And I explained the main problem, which has to do with the coordinate dependence on the quantities, and that we have to take care to not calculate coordinate artifacts, also called gauge artifacts in the linearized limit, and we only make a linear approximation. So there are gauge invariant quantities, which I will define in a minute. But what we did last time, and let me briefly review this, was that we made the ansatz of the metric writing as the background metric of a Friedman or Robertson-Walker line element, and we restricted ourselves to the flat case. And then we made small perturbations, delta g mu nu. Now, because of the symmetries of the background, we made use of transformation properties of the quantities under rotations and translations, and defined various quantities that are defined from the metric perturbations, but have a more direct mathematical meaning, and these were the scalar, vector, and tensor perturbations. So we have 10 degrees of freedom for the four-dimensional metric, the g mu nu, and for the perturbations we redefined the delta g mu nu by these transformation properties into four scalar perturbations called phi, psi, b, and e. They are induced by the density perturbations, by the energy perturbations, vector perturbations, which we neglect in the following because they decay rapidly, and our old friends from the lecture course on relativity, the gravitational waves, the transverse traceless components A, B. We are 2. So we have 4 plus 4 plus 2 gives 10. Now we neglect these, as I said, so we only have to deal with this and this. In this last lecture course, I actually focus on the scalar perturbations, and I will not discuss much about the gravitational waves, which in a sense is more straightforward than these scalar perturbations. So except for at the end we restrict to scalar perturbations, and I write down the metric for them, so scalar perturbations. So I have here, and I use maybe color to indicate the variables. So we have here the ds squared. So the scale factor is put outside here, and we use conformal time eta for that. This is why, I mean, it's a squared is outside. It's conformally related to the inside. So we have -1 plus, and then we have 2 phi. So this is the first term, the eta squared. Sometimes this is also called capital A in the literature. Literature is not uniform about that notation. But I used the phi because I used the same symbol also earlier in the Newtonian context. Then we have the b here, differentiated with in the xa coordinate direction, dxa d eta, and then we have the pure spatial part, which is written as follows. So 1 minus, and then we have 2 psi. So that's the psi here, delta AB, and then we have 2 times the remaining one, which is E, comma AB, dxa, dxb, No. No, so that's the part of the of the metric, including the perturbations, that only contains scalar perturbations, no? Which means that we have just set to 0 these remaining ones. Now, last time, or at the end of last time, I used the general transformation formula for the metric perturbations, delta g mu nu going to d g tilde, and because their definitions contain these perturbations, we can rewrite these transformation equations into transformation equations for the scalar perturbations. So I will not do this explicitly. I mean, you recall, I mean, we had, for example, delta g 0, 0 defined as minus 2 phi squared phi. Okay, this is what you read off here. And then we have also the g 0, 0 tilde we define as minus 2a squared phi tilde, and then by the usual coordinate transformation laws we related these two, and then we can also relate this, no? So, and for all others, and from this one finds, and I leave this as an exercise for you, or you can also read this in the books, that we have phi going to phi tilde is phi minus 1 over a, and then we have a psi 0 prime. Now the prime is the derivative with respect to conformal time, and just to remind you, we had here, I mean, x mu going to x mu tilde is x mu plus xi mu of x. Now this is the coordinate transformation that lies behind this transformation, and xi mu here we wrote as xi 0 and xi a orthogonal plus zeta comma a, where this is curl free and this is divergence free. This is why I indicate here this transversal. No, so just to remind you about that. And by doing this, and it's a straightforward calculation, so it would be boring to do it here at the blackboard, but let me just write then here what I get. So b plus zeta prime minus psi 0, and here we have then psi going to psi prime is a psi plus a prime over a psi 0, and finally then the e going to e tilde is e plus zeta. Now, so you see from these four components here, xi mu, which is xi 0, and then the three spatial one, only xi 0 and xi enter, and zeta, sorry, or only xi 0 and zeta enter. So only two of them, which means that I can, by an appropriate choice of them, set two of these four scalar variables to 0. So only the two xi 0 and zeta contribute. Not because I restrict here to the scalar part, when the others would enter the vectors and tensors. So I can set two of the four phi, psi, b, and e to 0. Or what I could do alternatively is to construct two gauge invariant quantities. So in a sense I have here two independent ones, because two of them of the four can be changed by coordinate transformation, and I can make a combination such that doing this here would not change them. And this was a big achievement to find this. Of course, there are various possibilities. The simplest are the followings, and they are called Bardeen potential. So simplest gauge invariant combinations. And these are the Bardeen potentials. Named after James Bardeen, who in a seminal work of 1980 introduced and discussed them, and really it has become standard to use them, because before that people always worked in certain gauges and sometimes did the right thing because intuitively they did the right thing, but sometimes they calculated coordinate artifacts. And so if we have a gauge invariant combinations, then we are on the safe side. And the two Bardeen potentials are defined as follow. So I call them capital psi, capital phi, and capital psi. Yeah. Sometimes also they are named differently, or they get an index B, like but for Bardeen, for example, phi B or psi B. No, but I will just have here the capital versions compared to the original versions. Yeah, so they are defined as phi minus 1 over A. You have A, B minus E prime prime, and this is here psi plus A prime over A, B minus E prime. So these are the two Bardeen potentials. And so please convince yourself that they are really gauge invariant. I mean, this is just a couple of 3 or 4 lines to check. I mean, calculate here the primed versions, and so you have to prime this, you have to prime this, and to prime this, and then you use this here. Yeah, so here the phi prime and the B prime and the E prime, and then you will see in 2 or 3 lines that there are cancellations, and that the capital phi tilde is the same as the capital phi without tilde. And the same holds for the psi. So whatever coordinates you use here, they are unchanged. This means in particular that if you have a situation where phi is 0, or a coordinate system where phi is 0 and psi is 0, then they are 0 in every coordinate system, because they are invariant. So if phi is 0 and psi is 0 in one coordinate system, they vanish in every coordinate system. This means if in that case, if you have a coordinate system where you have here some entries, it would mean that the corresponding metric perturbations are fictitious ones and not physical ones. In addition, I should also mention that there is a gauge invariant variable for the energy perturbation, because also energy perturbation is not by itself, of course, gauge invariant. It's just a component of a tensor density, but you can also form a gauge invariant combination. So gauge invariant variable for energy perturbations. Would be delta rho tilde is defined as, or I should maybe bar, is delta rho minus, this is the background energy density, and we have B minus E prime. No? So you have to invoke, of course, the energy momentum tensor and make its coordinate transformation. So you check then the transformation of this, and you check the transformation of this, and then you find that this is gauge invariant. Nevertheless, in spite of this advantage, it's often useful to work in particular coordinate systems, to work in particular gauges. And the two most prominent ones are called longitudinal and the synchronous gauge. So let me discuss them. So we have particular coordinate systems. So the first one is called longitudinal. Longitudinal or conformal Newtonian gauge. And how it is defined? It is defined by setting 2 of the 4 to 0, in this case setting B and E to 0. So it's defined by B and E setting to 0. So longitudinal means there are no transversal degrees of freedom. So in particular no vectors and tensors. So I mean if you had here B and E, I mean we had here B, the derivatives with respect to A here, and the E we have here the second derivative, so they would contribute so to the non-diagonal elements, and they are here set equal to 0. One can show that this fixes the coordinate system uniquely. No? One can show that this fixes the coordinate system uniquely, and so we have here then, I mean if you have here compare it with that, we have here then ds squared is a squared, and then we have minus 1 plus, okay, I should use maybe the same color here, 2 phi small phi d eta squared, and then we have here plus 1 minus 2 psi dx squared. Now where d vector x squared is just a shorthand for the dab, dxa, dxp. So this is what is left, and you see also why it's called conformal Newtonian, because it has this conformal factor, and otherwise it has this okay, this is the Newtonian potential, and at least in linearized gravity in the lecture course we have shown that this is the correct form. Now one can also show further, so if T mu nu, I mean the right hand side of the Einstein equations, is only diagonal, that then these two in this gauge are identical. So so if that is the case, which is often the case, then we have only one perturbation left. No? So then only one independent scalar perturbation phi is left or remains, And okay, this is then really the generalization of the Newtonian potential, because then we have here 1 plus 2 phi, and here also 1 minus 2 phi. In particular, we have then, of course, then that the capital phi is equal to the small phi, and this is equal to the capital psi here, right? This, you see here, the Bardeen potentials with B and E are 0, then, I mean, they coincide. This is a very nice property of the longitudinal gauge. So, which means that the gauge invariant potentials, really, they coincide with the potentials in that particular gauge. So that they have a direct physical meaning. No? So the gauge invariant potentials coincide with the potentials in this gauge. And so they can be interpreted. If you have some other gauges, of course, you have your other components, but they have no direct meaning. This is one of the two popular gauges. Actually, the most widely used one is not even that, but the so-called Synchronous Gauge. Synchronous means that it's a gauge such that dt is directly proportional to the proper time. Well, that's here written in the eta, but for the usual Friedmann time, proportional to proper time. So you set phi and b equal to 0. So it means you set all non-diagonal terms here to 0, where this is here 1, 0, 1, 2, 3. So we have here phi is 0 and b is 0. Okay, b is 0. This is also what we have here. So this coincides with that, but here instead of e equals 0, we have here phi equals 0. So actually, just as a side remark for those who know what lapse and shift functions are in the ADM formalism of general relativity, so this corresponds to the lapse function equals to 1 and the shift vector equals to 0. Yeah, so this is why it's called synchronous gauge, because time marches in steps, in equal steps, because the lapse is the gives you the change of the proper time with the coordinate time. Right. So, if you recall, in the Newtonian case, in our chapter 4, we have derived the equations for the cosmological perturbations, which at the end are generalizations of Poisson equation and the like. Of course, you should do the same here. That is, you should take Einstein equations and perturb them and use these variables. This requires some work, as you can imagine. I mean, you're not surprised that this requires some work, but of course this has been done long ago, and I will only sketch it. So we have here the equations for cosmological perturbations. So we linearize the Einstein equations around the flat Robertson-Walker metric. No? So linearize Einstein equations around the flat Robertson-Walker background. So for the background, I mean, I use here this symbol 0, the Einstein tensor in a mixed notation, one upper, one down index is, and I refer there to the cosmology part of relativity 2, can be written as this, where I have here introduced this curled Hubble parameter. This curled Hubble parameter, which is dimensionless, is defined as A prime over A, so derivative with respect to conformal time. And you can see that this is the same as A times H. Now that's our standard Hubble parameter A dot over E. No. Now you just have to replace d over dt by d over d eta, which introduces by definition the factor A. And I emphasize, so this is dimensionless, which is convenient to work with. Then we have the Gij turns out to be 1 over a squared, and we have 2 h prime plus curled h squared times delta ij, and we have 0 g 0 I, the spatial non-diagonal components of the equations are 0. The same you do for the right hand side. So we have here okay, we have an ideal fluid, and so we have 0 t 0 I is 0, and 0 g ij is proportional to delta ij. For consistency, of course, you know that, and so in particular here this is fulfilled here, and then you write, I mean, g mu nu is g mu nu the background, no, which is the collection of these three equations, plus delta g mu nu, and also t mu nu is the background plus delta t mu nu. And okay, you have higher orders that you neglect, so we only go up to the first order, the linearized level, and then we arrive at delta g mu nu is 8 pi g times delta t mu nu. So you relate these perturbations to these perturbations, but these are not gauge invariant as they stand, but you can construct gauge invariant combinations. And again, one makes a couple of calculations and convince oneself that the resulting combinations that I will write down will be gauge invariant. And these are the following. So we have gauge invariant combinations. For the details, I refer to the textbooks, Mukhanov's textbook, for example, in section 7.2. And these combinations are the following: dt00, they're called bar, which is the t00 minus, and we have here the background t00 prime, and b minus e prime, and also other energy momentum tensor components. I don't bother you, I mean, to write to read all of this. I think what you have to understand is that one with profit uses such combinations which are gauge invariant. And also the first one of the Einstein tensor is delta g00 minus, then also the background g00 prime, and again you have this similar here to the other side for consistency here, and also the other components. Now you can read them in the books, and you can just convince yourself if you make this coordinate transform formation and use these relations. Yeah, that I mean the transformation of this b minus e prime so on will just cancel, and they are invariant. So that you have here, then you can write the Einstein equations in gauge invariant form. So using this gauge invariant perturbations and gauge invariant Einstein tensor and energy momentum tensor, we can write delta g mu nu bar is equal to 8 pi g times delta t mu nu bar. So this would be then the central equations. So what do you have to do? I mean, you have to insert now here. I mean, it contains the metric, including the metric perturbation. So you have to include the ds squared, the metric components from the ds squared here in this, and calculate. And then you find here from this equations for the scalar and vector and tensor perturbations. And if you restrict again to the scalar perturbations, I get the following equations. So inserting, I mean what we have from the ds squared and so on, one finds for scalar perturbations only the following. Of course, again, it takes some time, I mean, to calculate. So we have here, so it's written here with respect to the gauge invariant Bardeen potentials. So you have here Laplace psi, capital psi, minus 3, the curled h, the dimensionless Hubble parameter, which is a prime over a. And then we have here psi prime plus h phi, so it's the other potential, is 4 pi g a squared times delta t 0, 0 bar. Now, so let me call this the equation 1, which comes from the 0, 0 component, obviously. So generalizing Poisson's equation, if you like. And then we have from the 0i equations psi prime plus h phi comma I is equal to 4 pi g a squared delta t 0i bar, which is equation 2. And then we have the last ones, which is of course a whole set of equations, psi double prime. Yeah, and these are constraint equations, so we have here the time derivatives only to first order, but the remaining ones have time derivatives at second order. Delta ij, well, it's not clear whether I have to write them down. Okay, maybe just that you see them. Then I can do the following: plus h 2 psi plus phi prime plus 2h prime plus h squared phi plus 1/2 Laplace. Then the difference between the two, delta ij minus 1/2 phi minus psi comma ij is equal to minus 4 pi g a squared delta t ij bar. No? So all of this then is a bit more lengthy, is then equation or set of equations 3. So you see, that's actually what we wanted. We wanted to have a set of equations for gauge invariant perturbations from the Einstein equations. If we go to the longitudinal gauge, then you already have this form, the longitudinal gauge, the capital psi is the small psi, and the capital phi the small phi. So this form, without any modifications, you have also in the longitudinal gauge. In other gauge, of course, you have to then insert the corresponding, expressions that relate the capital psi to the small psi, which has some additional terms. So for the energy momentum tensor, of course, we use the high form of hydrodynamical perturbations. Hydrodynamical perturbations, because already for the background we are forced, to have the ideal fluid expressions. So we use the form that T mu nu, the full T mu nu is rho plus P u mu u nu plus P delta mu u. Okay, so if you have this, calculations then show that capital psi is equal to the capital phi, and that we can simplify these three as follows. So here, calculations show that psi then is equal to phi, as I mentioned earlier, and they simplify here, and I probably don't write down all. So 1, 2, 3 simplify. So for example, equation 1 becomes then Laplace phi minus 3 h, and then we have here phi prime plus h phi is 4 pi g a squared delta rho bar. So you see here from this that for static universe, if you had one, this here would be 0 because h would be 0. There would be no expand. So for static universe, you would just have Laplace phi is 4 pi g a squared delta rho. So of course this would be constant. So you are back to Poisson's equation for the Newtonian potential. So you see how these complicated things, for general relativity, are related to, say, the old Newtonian limit. Of course, this is not to be confused with Newtonian theory, but in this linearized regime and for a static universe, you would have again something like the Poisson equation. No? So this would be 0 for static universe, and then we have back the Poisson equation for the Newtonian potential. Phi. Yeah. So again, we can define the speed of sound and the parameter sigma. So if we have the pressure perturbation gauge invariant, we can define the Cs squared by relation to delta rho bar, and also we have this dependence on the entropy perturbations. So as before, here this would be dp bar over d rho for constant s, and this sigma would be dp bar over ds for constant rho. And with this you can write equation 3 in a way where you see its generalization to the earlier Newtonian equation, where we had this speed of sound and the sigma parameter. So then you find from this here that phi double prime, no? So second time derivative plus 3 1 plus cs squared h phi prime. Of course, we did not use the curled h, but you recall perhaps that we had a term with h phi dot at that time, minus cs squared Laplace phi plus 2 h prime plus 1 plus 3 cs squared h squared phi, and this is the Bodine potential, no, to recall. This is the gauge invariant potential, is 4 pi g a squared times sigma times ds. No? So go back in your manuscript or in the book to the Newtonian case and maybe take a couple of minutes just to look at the two equations and to compare them and see the difference. No? So here, that's in a sense what we wanted as a result of this chapter 5, the generalization. This is the generalization of the Newtonian equations in the previous section. Okay, now, I mean, this could now be used as a starting point for a lot of discussions, I mean, to make special cases, to, for example, discuss just the adiabatic perturbation, setting this to 0, discussing entropy perturbation, and so on. So there's a huge specialized literature, and I'm afraid the semester is practically over, and we cannot discuss all of this here. But I think if you understood here how we arrived at this, then it should be rather straightforward to go to the textbooks or to the literature and understand what one can do with this and what are particular solutions. Of course, you have to do then solutions of differential equations and the like. But you see here, this is from the Einstein equations, an equation for perturbation, for gauge invariant perturbation that is important for density perturbations in the universe. Instead of following this here further, and I could talk hours, of course, many hours about that, I will here in the remaining time have a brief final chapter coming back to inflation again. Also, this would in principle take a lot of time, but I will at least sketch what is done here, namely in inflation. You recall that we have for the homogeneous version, in the very early universe, 10 to the 34 seconds or something like that after the Big Bang, a rapid quasi-exponential expansion of the universe to solve various problems of the old models, particularly the horizon problems. Now, the modern understanding is that at this early time, I mean, all the perturbations we deal with for the metric and for the matter are quantum perturbations. That even if we start, and this is usually assumed in the vacuum state, we have, of course, also for any quantum field, we have contributions from the vacuum. And I will at least want to at least sketch this here, and so that's a brief summary of what I call inflation 2, so the quantum origin of bimodal fluctuations. Let us have a look at the various scales. So this is just a sketch. So if I have here co-moving scales, where the scale factor is factored out over here the logarithms of the scale factor, you can say that's over time. And so a density fluctuation maybe has a fixed co-moving scale. It just scales with the scale factor. So it's here this straight line. So a density fluctuation. And so let us sketch then here the co-moving Hubble scale in this. Now recall what we had before. We had a co-moving horizon, which is just the integral over dt, the integral dt over a of t, which you can rewrite as follows. You can write this as integral from, say, some initial to a, and then we have d ln a 1 over a h. That's the co-moving horizon, which it just with respect to t is integral dt over a of t. And it's written in this way because here this one is very important. This is called the co-moving Hubble scale. No, the Hubble scale is just the 1 over h. We had also discussed this before, and this is then the co-moving one, which which is co-moving Hubble scale. So it's a h to the minus 1. So, and for example, for the radiation-dominated universe is proportional to t to the 1/2, because this is proportional to t to the 1/2, and this is proportional to 1 over t for radiation dominance. So in this diagram, I mean, if you have inflation, so we would have a decrease of this, say up to here, and then an increase. No? So that would be the co-moving Hubble scale, h to the minus 1, which would be here, that would be the radiation dominated part, radiation dominance, and this would be inflation. Now inflation, the h is just a constant, and you just have this decrease with 1 over a, which is in an exponential decrease, which here in this logarithmic plot is just then this decreasing line. No? So we have here two distinguished points, and these are the 2 points where this scale exits the Hubble. Where this scale that we have here, it's smaller than the Hubble scale. So, but here it becomes bigger. So this is called, loosely people sometimes talk about horizon exit. It's in fact it's the Hubble scale exit, and this is the combination that is actually relevant for discussing inflation. And here we have this re-entry. And you see here in this diagram the solution of the horizon problem. No? Without inflation, only having radiation dominance, then, I mean, this would here go to the Big Bang. And so you would have scales that were just outside of this and would not, I mean, concerning the Hubble scale, and this is really related to the horizon itself, it would not have the opportunity for causal contact. So you would never understand, I mean, the spectrum of these fluctuations that we observe today. I mean, you would just here enter at some point, it would be there as an initial condition. But here you see inflation gives us the means to understand the causal origin of that. And these scales here, I mean, here we have small scales here that small scales. They were much smaller than here, this Hubble scale, and we can write as k is much bigger than h. Now, so that's the dimensionless wave number, where a is factored out, and it's the inverse of the wavelength. So small wavelength is big wave number here. So here. Now here, how do you describe this density perturbations? I already mentioned that we assume that because the universe was extremely small and there was no classical matter, but that they are in a certain quantum state. No? No. So assume here. So we assume that these perturbations or scales are described by a quantum state. And if we don't have interactions between these various perturbations, and because they are small, we assume they are just free oscillators. So we have, as in quantum field theory, I mean for the vacuum, it's just a set of infinitely many harmonic oscillators. So we have here the ground state. So we have a ground. So assume ground state, which is infinitely many harmonic oscillators. So we describe them as usual by annihilation and creation operators. So we have a vacuum that we in the standard language call zero in the Dirac notation, and we have a annihilation operator here for any mode that is here much bigger than AH. And we call this vacuum the adiabatic vacuum, or we choose that. I mean, it's not unique, the adiabatic vacuum, because we assume that for co-moving observer, locally it looks like the Minkowski vacuum. So if we have eta, the conformal time going to minus infinity, and for k much bigger than AH, it's the Minkowski vacuum. Minkowski vacuum. I mean, co-moving means we don't have acceleration relative to this, otherwise you would get Unruh temperatures. So in the far past, which means eta to minus infinity, and of course for the very small modes. Sometimes people refer also here to the so-called Bunch-Davis vacuum, but especially for massless modes, this is not exactly what the Bunch and Davis discussed. So it's better to just call this adiabatic vacuum. Now, because this is just a brief review, let me mention that we can construct a gauge invariant variable that is called co-moving curvature perturbation. So gauge invariant co-moving perturbation that is defined as from the Bardeen potential in this form. So that's phi naught is the solution, phi naught of t of the background, the evolution of the inflaton field, and this here is the perturbation of the scalar field. So that's the scalar field. I mean, I want to avoid confusion with the potential, so I don't write a capital phi here. So yeah, this is one important definition here. One important variable. So okay, if you didn't have a scalar field, then it would just be our psi, but with the scalar field. I mean, it's combined here. And in addition, an important one for this variable, the so-called Mukhanov-Sasaki variable. For the scalar modes, and it's mostly called V, which is defined as Z times R. So it's related to this, but this Z is defined, or Z squared, as A squared phi naught dot squared over H squared. Now, so that's also gauge invariant, and in Fourier space, it's just V key, so Fourier space. So that's also another important combination. Okay, so that's here. These are, I mean, conveniently introduced gauge invariant quantities for the situation where you have scalar perturbations for the metric and for the inflaton field. Now, at least I mention a little bit also the tensorial modes, the gravitational waves, because they can also be nicely accommodated here. So for the tensor modes, so we decompose the HKL, I mean the tensorial perturbations, into Fourier components. HKS, I mean for the two transversal polarization states, the cross and the plus polarization, and okay, the components are in the polarization tensors, no? Like in relativity 1. And when we define the following VKS as okay, A over square root of 16, so this is of course just for as a convention, HKS. Then this VKS, S1 and 2, they are very similar to these. So in a sense, you can consider these tensorial gravitational waves, these perturbations, as two scalar perturbations. Essentially, two copies of this here. So these are essentially two copies of the VK. Now you can expand them into the plane waves, because we are in a flat spatial universe. So the V of eta, which is here that, no, that's the same V, so I should write it, is integral d3k over 2 pi cube, and then we have here Vk of eta. Maybe I just I can here add this tensorial of ak hat e to the I kx plus Vk star of eta a dagger k e to the minus I kx. So that what you would do in the Heisenberg picture, where you just have these operators here, time-dependent operators that you expand into terms with a creation and annihilation operator. No? So that's the Heisenberg picture. In the Schrödinger picture, of course, you have time-dependent quantum states. So we have wave functions. So again, a psi. So this psi is a different psi. It's not a potential or perturbation. It's a wave function that depends on the Vk and eta. No, so that's the wave function. Of course, you have a wave functional, because we are in quantum field theory, for all these infinitely many modes, but in the linearized approximation, the various modes decouple. So you have infinitely many wave in a sense, quantum mechanical wave functions psi k. And because we have the ground state of an harmonic oscillator, we have a Gaussian that you can write here as such, omega k of eta and absolute value of vk squared. So that's Heisenberg picture. That what is often used here. So that's a Schrödinger picture. And okay, for one oscillator you have here this 1/2, and is the frequency. But here the Vk, they are actually complex, so you have the real and imaginary part. This is why I have written also here the absolute value. So you have the real part squared plus the imaginary part squared. But essentially this is the ground state of the harmonic oscillator. And if you take this as an initial condition here, then of course you have to evolve it. And you have to evolve it at the background of this expanding universe, which is first inflation and then radiation dominance. And if you do that, I mean, you have to solve the Schrödinger equation. Well, I h bar psi k dot is hk psi, and you have here the Hamiltonians that you write down for these modes. Then you take that as an initial condition, but because of the expanding universe, they will not stay in the ground state. Actually, they behave in a way that you perhaps know from quantum optics, namely they stay Gaussian, but this here develops an imaginary term, imaginary part, and it corresponds to an excited state. You can write as an infinite sum of all the excited states of the harmonic oscillator. Actually, it's a so-called two-mode squeezed state. So if we have only this, and then also then later, then if we have an excited state, sum over excited states, and actually it's a two-mode squeezed state. So you see how here microphysics and macrophysics come together. We are in cosmology and the universe as a whole, but you need here quantum optics to understand the evolution of this primordial perturbation. And they are all quantum, but this is not what we seem to observe. So there's also a quantum to classical transition involved, which is a subtle feature. And it would take me too long for the details, so it's also called, the process of decoherence. So that, these quantum variables assume classical properties. If you like, you can read an essay of us, so together with a colleague from France, David Polaski, and so some years ago we summarized this, so you can read this on the archive under this number. And also then there are references to the original work. Okay, so how do you then get the final power spectrum? You would then relate this to the power spectrum of the CMB that you observe, the density perturbation. So how do you get this from here? We have these curvature perturbations R, and if you go to Fourier space, then you have RKs, RK prime, and then you calculate a two-point function. So these are quantum expectation values. So quantum, and so this defines the power spectrum. There are some factors, and also there's this correlation that K is equal to minus K prime. I should say here, this two-mode squeeze state here in the Schrödinger picture corresponds to particle creation here in the Heisenberg picture. And the particles are created in pairs here, and this is why k is equal to minus k prime. If you create pairs from the vacuum times p r of k, and we define then, okay, this is already the power spectrum, but it's more conventional to use this and separate a factor k cube and from this. Okay, I need just a little bit of space. So now you have to do an explicit calculation. Now here you have to insert these states, but with the time evolved Gaussian, yeah, not just the ground state, but with the omega. So you can, so you know how omega k looks like. I mean, it's from the solution of the Schrödinger equation, and this is the nice thing. You have small perturbations, and you work with Gaussian quantum states, so you can do everything. I mean, on paper, you don't have to resort to maybe complicated numerical calculations to do that. And then, so we find then the following. So from this, we have then that delta S squared of k is 1 over 8 pi squared tp h squared times epsilon v to the minus 1. So what are these? I mean, okay, this is the Hubble parameter, which is actually, this is evaluated at the Hubble scale exit at this point. So, okay, at exit. And this TP is the so-called reduced Planck time. So TP is the square root of 8 pi g h bar over c to the 5, which is the reduced Planck time. Actually a scale from quantum gravity, very small, of the order 10 to the minus 44 second. H has dimension 1 over time, so this here is dimensionless, and this we had earlier. So this is the one of the slow roll parameters. EV is 16 pi g to the minus 1 v prime over v squared. But this was the inflationary potential, and this is something that is determined from observations. I mean, from the CMB and from the Planck satellite, and it turned out that this is 2 times 10 to the minus 9. So that's from observation. So you see here a nice combination here of, say, of this of the inflationary phase, but also with effects that come from, at the end, quantum gravity. Because also here we have not only the scalar field, but also metric components. I mean, the scalar metric components are here involved, and they are used here as quantum variables. No? So here this is quantum. You have here annihilation and creation operators, and so also this includes metric perturbation. So you could call this already at least a linearized quantum effect of gravity. So that's what you have here. Also for the tensor perturbations, you can do the same. You can have also the expectation value hk prime, and you can define, okay, this is 2 pi cube delta of k plus k prime prh of k, and again we can have this delta s. Here is delta h squared of k, which is k cube over 2 pi squared times p h of k. And the explicit calculation here gives, so the calculation of this expectation values gives, well, I actually, it's usually the, we have the delta tensorial squared, which is defined as twice this here. That's what usually people give, and this turns out to be 2 over pi squared and Tp h squared. And so you again have this combination here. Compared to here, you see here both the tensorial and the scalar perturbations, they have this essential factor Planck times Hubble parameter squared. Actually, this was already calculated long ago by Starobinsky in a famous paper of 1979. I mean, before the advent of inflationary scenarios where you had the zeta space time and calculated the generation of gravitons, if you like. This would be the Heisenberg version of that Schrödinger version, the generation of gravitons from the vacuum. That's a very important result. And of course, this is what we observe from the CMB. Can we observe this directly? I mean, some 8 years ago, there was a big excitement that perhaps it was already detected by an observatory at the South Pole, BICEP 2. It has turned out that this was not the case, but was some more or less some dust perturbations in the foreground. But nevertheless, I mean, search is going on to look for not direct measurements but indirect hints, contribution to the polarization of the CMB of this, and this would then be a direct window to quantum gravity, because here you could say, well, there's also the scalar field there and it's not so direct, but here you have gravity proper and you have a quantum decrease proper, at least at a linearized level. Now, a famous parameter that has to be determined observationally is this parameter r, which is delta t squared over delta s squared, and which from these expressions is 16 times epsilon. Now, so the bigger the r is, of course, the more prominent are these tensor fluctuations, and in this BICEP 2 measurement it was already concluded there is a certain r value bigger than 10 or 20, I don't remember, which would correspond to observation of this. But so far we have only upper limits for r, and search is going on, I mean, to detect r. Well, but this is another story. I mean, if we know r, we knew, or if we knew r, we would know the scale of inflation. So knowing r would give the scale of inflation, the energy scale of inflation, because one could then calculate, I mean, this is because this is already fixed, and this would be also then given. So energy inflation would then be 1.06 times 10 to the 16 GeV if you have r in units of 0.01 to the 1/4. So after some calculations from these things, you could, if this were measured, you would then really know when inflation took place. Okay, this is more or less the end of this lecture course. What I did not do, also because of lack of time, is to calculate here directly the spectrum of the CMB anisotropies. Now you have to, they are, they are temperature fluctuations, no? So CMB anisotropies. So you have to relate, I mean, these primordial fluctuations, these power fluctuations into, translate them into temperature fluctuations. Now, this I have no time to do, but if you like, you can read in these excellent books by Mukhanov or by Peter and Husson the details of that. I hope it's clear that still there has to be some work done. And perhaps I should also say that, this opens the window to quantum gravity, and there will be a specialized lecture course by myself next semester, starting beginning of April, on quantum gravity. So we will of course discuss quantum gravity in general, but I will also make the connection here to this and try to show how this framework also comes out as a limit from a, well, still hypothetical quantum theory of gravity. Okay, before I close, I should also thank my PhD student, Tadevik Vardanyan, who without her I would not be able to do this because she's always behind the camera and also editing it so that you can see it and watch it. And at least at the end I would give her the opportunity to also show up here. So please, and thank you very much for your help.